Hello? Hello?
Yes, ma'am.
Okay.
Good evening, sir.
Yeah, good evening.
Sir, good evening.
Good evening, Professor Nilima.
Sir, good evening.
Sir, we will start sharp at 4:30, so there's 7 more minutes. So we'll wait for the participants to join. I think they are joining. So it's 4:30. We'll start. Sir, shall we start, right? Hello?
Yeah, I'm fine.
I think, sir, people
Nilima.
will, yeah. So the participants will start joining.
Okay.
And I think we will start on time. So, good evening, everyone. So nice to have you again today with our lectures. So we have two speakers today. So first one is Dr. Meghna Sharma. She's right now DST Inspire faculty. And also I'm very proud to say that she was my former PhD student at IIT Indore, along with me. Professor Reddy also supervised her. So it is great, for me to have her here as one of the speaker today. And we have a second talk by Reddy sir. And I hope you had a great time yesterday. So we are recording the lectures and it will be shared in IGS YouTube channel, and which we will share the details with all of you. Before going on, I have one announcement. The certificate will be issued for the participants who attended all the 5 days. So kindly bear with us. And the second thing is, like, the feedback form will be shared on the last day. Before that, we are planning to share one Google form wherein, like, you can post your comments, suggestions, queries, whatever it is, so that we can go through that and help each other, so that we can discuss and have a collaboration in future. So with this few words, I'd like to start the second session with the request from Sir Reddy sir. You have anything to say? So please, sir.
No, I don't. I don't have anything to add on. So
Yeah.
please go ahead.
So, Nikhil.
Yes, ma'am.
Okay, so can we start, please? Nikhil, are you there?
Yes, ma'am.
Please start.
Hello, everyone. I'm from GeoGards lab at IIT Indore and would like to call Dr. Meghna Sharma, madam. Ma'am is an institute postdoctoral fellow in the Department of Civil Engineering at IIT Bombay. Ma'am has recently received the prestigious DST Inspire Faculty Fellowship. She completed her PhD degree in civil engineering from IIT Indore in August 2021. Based on her research, she has published one Indian patent, 14 journal articles, and 4 conference papers. 3 articles are also under review from her postdoctoral work. She received the Springer Best Paper Award for the paper presented in IGC 2021 and Best Research Paper Award conferred by IIT Indore for the academic year 2020-2021. Her research published in renowned journals in some, like, for some examples, engineering geology, elsewhere, Journal of Rock Mechanics and Geotechnical Engineering, Toxic and Radioactive Waste, ASCE, International Journal of Damage Mechanics, Sea Journal, and Journal of Soil Use and Management. Most popular articles or most cited articles in last 3 years. Prior to it, she completed her MTech in soil mechanics and foundation engineering from the NIT Kurukshetra in 2024. She received gold medal for being the best graduating student in MTech and had the honor of receiving this award from the former President of India, Dr. APJ Abdul Kalam Sir, during the convocation in 2015. Madam, I would like to start the meeting. Thank you.
Thank you so much, Nikhil. Thank you, ma'am. Thank you, Reddy sir. So is my screen is visible?
Yes.
Yeah, it is visible.
And then,
Yes.
yeah. Thank you so much for inviting me, ma'am, for this lecture, and I'm like very happy to present today this. First of all, I'd like to acknowledge Nilima ma'am's support and Reddy sir's support throughout my PhD and even after that. And today I'm going to present like mechanism and application of microbially induced calcite precipitation. So basically, first of all, what we need to see, what are the challenges associated with the ground and the geoenvironmental applications. Our theme is hazard mitigation and environmental protection. So with the geotechnical challenges associated, in that case, what we can say, like there are challenges, like we can say there are failure images, liquefaction, you can see the leaning tower of Pisa, and this is due to the earthquake, and this is ground subsidence, and landslides are there, and due to wind erosion, due to riverbank erosion. So these are various geotechnical challenges which needs to be addressed. Okay, so to deal with these, and we can see like latest example, there was like Assam earthquake in 2021, and liquefaction was there, and in the earthquake there are various like structural failure also, and sometimes the structural failure occur because of the ground challenges. So there are several soil improvement methods, like conventionally we use like jet grouting, soil reinforcement, and soil replacement. And recently I was working at IIT Bombay as an institute postdoctoral fellow. So at the Mangalore terminal, like there is a storage tank construction site, and there at that site, the challenge was the liquefaction, like that the site is of liquefaction prone. So in industry, generally, they were providing the vibro stone columns. Okay, so Tata consultants were there as a consultant, and Kaler were doing the work there. So the vibro stone columns are provided. So just we like when we do the research, we need to know also like what our industries are using in the field, and what we are doing in the lab, and how can we take it up to that level. Okay, so that can be applied to the field. So like these are the conventional method, but sometimes like we use cement for grouting, and these are like or chemical grouting is used. So sometimes like either the manufacturing of cement create, we can say at the manufacturing stage, it creates environmental hazards and all, and if use the chemical thing, and that can contaminate the water. So either at the manufacturing stage or at the application stage, the hazards are there. So due to the carbon intensiveness, and if you have heard about the sustainable development goals suggested by UN and UN, United Nations, and there are 17 goals are there, and we need to achieve that by 2030, I think. So for that, we need to work on the zero carbon emission, and environmental friendly approaches needs to be used, and we need to use the economic and sustainable ground improvement method. So after a lot of research, like there are few advanced methods also, like supplementary cementitious materials are used, biopolymer, biochar, nanomaterial. But with few of these, there is a challenge of either these are costly or it is challenging to apply it to the field. So uh, uh, and after that, along with the geotechnical challenges, we have the geoenvironmental challenges also. Like our soil is degrading. Like if you heard about the Save Soil movement started in India by the Sadhguru, so that is because of it only. Like we are harming the soil with the mining activities and electronic waste. This is the recent thing we are doing. Okay, in agriculture, we are using the pesticides right and left, and that's how the soil pollution occur, and thermal power plant waste. So the fly ash was earlier a great problem. Now fly ash is using for the concrete manufacturing and road manufacturing also. So reutilization is required. So household waste and plastic waste. So these are the geotechnical and geoenvironmental challenges. Now, how do we deal with them? And now what should be done? Like on which topic I worked on, that is the microbially induced calcite precipitation. But that idea also comes from the nature. That's why we call it the nature-based solution. Nature-based solution means which is the based on the nature's biology. Okay, so how this microbially induced calcite precipitation is depends on the nature's biology. Like in general, how the rock forms. Okay, we know the process of from the rock how the soil form. Everyone knows it. Okay, like due to weathering, physical, chemical weathering of rocks, the soil forms. But from the soil, how the rock forms, that is a different process. Okay, so nature's biology play a critical role in this, and the bacteria act as a geologic agent to form the various geological structures, okay, and earth structures. So in that case, we can say natural lithification is the reason for the formation of rocks, or we can say the time dependent ground improvement. Like there are several examples in the all over the world. There is a Nambang National Park, you can Google search it, Nambang National Park in Australia. Okay, so there also, like mud after wind erosion, the pinnacles came. Pinnacles are the calcite precipitated sand. Okay, so these pinnacles came into the existence. Like this here in Jammu, also in Ladakh Valley, wind eroded pinnacles came into the existence. Means there is a wind, there is a soil all over there, and after wind erosion, these pinnacles came into the existence. Similar to that, in near the riverbed, this one and this one in Spiti Valley, Lara and Dhar, these pinnacles, mud-capped pinnacles, came into the existence. Okay, so this shows like with the time the soil converted into the rock. But how it goes, like how many years it takes to convert the soil into the rock or to into the hard strata, which we need to for the construction of a structure, because on the loose strata we cannot construct the structure, right? Okay, so to construct any structure, we need the hard strata. So how this strata naturally takes millions of years. Okay, but this concept, this mechanism can be applied artificially into the laboratory, and we can get this process in hours. Okay, so this, like I would like to elaborate the mechanism of it, the basic things I'll discuss over here, okay, and few major results of it I'll discuss. No, we will not go that much technical, but I'll overall I'll give you overall view and overall results, like what can we do and what can we get. Okay, so that clear perspective you will get it. So in the like in the soil, there are porous spaces, okay, and in between, like the sand particles are discrete. If we talk about sand here, okay. So when to execute this process, bacteria must be required. So bacteria, it should be urease producing bacteria, and if the bacteria is already present into the soil, then its growth should be simulated. So that is known as biosimulation process. Like if urea is producing bacteria is already present into the soil, and there are several tests to know it. Okay, we can know it by like DNA and PCR sequencing methods and various other methods. So gram staining method. So if we found the urea producing bacteria into the soil, then our half of the problem get resolved, because we just need to provide the nutrients to the soil and its growth, bacteria growth will be simulated. Then we can provide the other reagent solutions. Okay, so that is the biosimulation process. And if in any case the bacteria, generally these urease producing bacteria are soil based bacteria only. So if in any case the bacteria, urease producing bacteria is not present into the soil, then bioaugmentation is required. So augmentation means we are culturing the bacteria somewhere else and we are providing to the soil. Okay, so we give some time to the soil to get adjusted with that bacteria, and bacteria get attached with to the soil, so that the further biochemical reactions will take place, or we can provide the reagent solution to strengthen the soil. So after getting done with the bacteria thing, like either biosimulation or bioaugmentation, after that the reagent solution and its concentration, its amount, how much duration it should be provided, and up to how many days it should be provided, these all things play very, very important role in this process. Okay, so urea and calcium chloride dihydrate, these are the two major resources of it, and urea can be sometimes replaced by the agricultural grade urea, sometimes and in the calcium calcium source, a few sands are calcareous sands, like desert sands are calcareous sands. So that also help in the calcite precipitation thing. The amount of calcite precipitation and bonding will be higher when this process is done. So in case of wind erosion thing, it is very much helpful for calcareous sand. And sometimes industrial waste of calcium source can also be used as a substitute of calcium chloride dihydrate. And nutrient growth is also plays an important role. Nutrient growth is, the name is quite fancy, but in simple word, if I can tell you, that is the food of bacteria, because it's a living thing. You are working with a living thing, you are not working with a dead thing. So it's a living thing. That's how it is. Food is necessarily required, and buffer solution to maintain the pH. As sir also said yesterday, like pH plays an important role in these kind of reactions. Okay, so generally for these reactions to execute or to get the calcite precipitation, generally 8 to 9.5 pH is required to get the significant amount of calcite precipitation. And if the pH is increasing, we can get to know these reactions are going on. So this is one of the major. And I said like soil type is important, like sand in clays, we have the different strategy. In alluvial sand, we have the different strategy to teach in treat. And in arid region like desert sand, like we need to do the wind erosion, so we should have the different methodology to treat. Okay, then it depends on the bacteria type also. Even I worked on 3 types of bacteria in my research, and it was like all bacteria have different type of activity. Okay, one is a spore forming, so highly spores are getting from them. The main, higher the optical density or higher the density of bacteria, higher is the calcite precipitation we can achieve. So bacteria, then temperature. Okay, there is a like 25 to 60 degrees centigrade temperature is required or maintained, can be maintained, or in that this reaction can be executed. Okay, pH and the pore water chemistry of the reagent solution. So what happens basically in when we provide such things into the soil? Okay, so urea, in presence of urease enzyme, produces ammonium and carbonate ion, and that calcium ion get attached with the bacteria cell. Bacteria cell is negative. Okay, so bacteria cell, and then it produces the cell attached calcite precipitation in between the porous spaces of soil, and simultaneously enhances the strength of soil. Okay, so like like I conducted initially a small scale study to analyze like what will be the effect of different concentrations of urea and calcium chloride dihydrate. What will be the effect if I treat it up to 14 days duration or 28 days duration, and with different types of bacteria. But there was a simple procedure, like I provide the bacterial solution to the sand and kept it for few hours, and then the reagent solution was provided in every 12-hour of interval, and then this calcite precipitation was achieved. Like this simple sand and untreated sand got strengthened, and you can see that cylindrical specimen. Okay, so as visibility also we can analyze like the sand particles got bound. Okay, so a scanning electron microscopy was carried out, and through that through this method especially, one thing is very interesting, like we can see the microbe bed also where the microbe was present, so it can show like microbe attached calcite precipitation. Okay, and in all figures you can see there is presence of calcite crystal. Okay, so ultimately all combinations worked, and the calcite precipitation was achieved in all the combination with Sporoscarcina pasteuria bacteria, with Bacillus subtilis bacteria, and Bacillus sphaericus bacteria. You might have heard about the Sporoscarcina pasteuria bacteria because it is quite knowingly used. And I want to check the potential of other two bacteria, Bacillus subtilis and Bacillus sphaericus, because if these two are present into the soil, then what will happen? Okay, because these two are also soil based bacteria, so we need to check that. Yeah, so after that, like XRD analysis, through the XRD thing, like untreated sand have only quartz peaks, so that means it was only pure quartz sand. And in the estuary, in the subtilis, and in the sphaericus, every bacteria augmented sample is having the calcite precipitation peaks. So the calcite precipitation occur in every bacteria combination, and whatever treated up to 14 days or 28 days, both. And through the FTIR analysis, the peaks of the bands of, we can say, the presence of ammonium, like through these bands, the ammonium presence was observed. If the ammonium presence is observed now, it means the biogeochemical reactions happened. Okay, and CO stretching and OCO bending confirm that the carbonate precipitation is there. Okay, so all these methods will help you out to know that the precipitation occurs and that particular type of mineral occur along with quartz, the calcite precipitation occur. And then the main important thing, that how much calcite precipitation through the SEM analysis, through the XRD, through the FTIR, we know that the calcite precipitation is there, but how much and what is needed? What is our requirement, like what we generally need for strength improvement, for a strength of to improve the layer strength of soil, like soil is in layers, okay, at the ground. So to improve as a layer, what we need the uniform calcite precipitation. If we go for wind erosion control, then what we need the surface crust to be thick, so that the wind erosion can be mitigated. So here in this like study, what I found is like all bacteria worked well. Okay, so Bacillus subtilis and Bacillus asphericus can be used as a substitute of this especially, but the coming to the concentrations, okay, of urea and calcium chloride dihydrate. So the equimolar concentration of urea and calcium chloride dihydrate with 5.50 molar concentration resulted in uniformity in calcite precipitation. Means the this whole depth get precipitated, okay, and in other samples like where the ratio was like urea concentration was higher than the calcium chloride concentration, in that only at the top layer the precipitation was there, at the bottom layer there was very less precipitation, okay, 1-2%. So that's why like we need to choose like what is our application, where we need to apply, how or why this is so. This is because of the rate of reaction, because if the urea amount is higher, the rate of reaction, the pH will increase significantly at a faster rate, and the precipitation will happen quickly and it will create the bioclogging. Okay, and if the rate of reaction is a bit slower, or there is a constant pace in that, okay, if we use the same amount of urea and calcium chloride dihydrate concentration, so in that case there will be uniform amount of calcite precipitation. So this is one of the challenge of this MICP method which we worked on, and we got the solution for that. And after this small scale research, after this, like there are several studies were carried out, laboratory studies in which we have prepared the cylindrical samples and tested for strength, ultrasonic pulse velocity, triaxial testing, and even dynamic testing tests were also conducted, and durability was also investigated. So after all these things, laboratory investigation, we need to go to the model scale testing or large scale testing. That was our major aim, so that we can provide the solution for this method. Okay, so I'm skipping those intermediate studies where I worked on the durability and other things and strength improvement criteria. And now I'm moving forward to the model scale application. So I'm very happy to say that, and I'm thankful to ma'am. Like we just last week we get to know that our patent is going to be granted on this study. Okay, so we are about to get grant on this study. So this study was designed in such a way like if the bioaugmentation is required in the field, then how can we cultivate the bacteria? Okay, if the urea producing bacteria is not present to us, then in that case, and if we want to achieve the uniform calcite precipitation, we need to provide the solution uniformly. The another challenge. Okay, so we inspired from the tube A manchete technique, the slotted injection pipes were provided. Okay, were used, and then third thing, anaerobic condition at the great depth. That was also the limitation. So to avoid the anaerobic condition at the great depth, we provided the air pumps. Okay, air asparaging, biosparging. We called it biosparging. Okay, so air asparaging was done through the pumps. Okay, so this is the whole setup. Like this is a biotreatment tank. Okay, where the sand was 1.21 ton sand was placed, and at 40% relative density, and this was the bioreactor in which the bacteria was cultivated, and this is the chemical solution tank in which we mixed the say urea, calcium chloride dihydrate, and everything, nutrient growth, etc. So the pumps and motors are provided to circulate the solution, and these injection pipe, 9 injection pipes were used at a particular spacing so that the solution can be provided throughout the tank and throughout the depth of the tank, and these air pump for biosparging, and these are the drainage pipe to collect the solution. So this is the actual setup, okay, which we developed. And for the bioreactor, like it was designed in such a way, so we covered it from outside so that inside temperature can be maintained, because bacteria should be cultivated at a significant, like we maintain 30 degrees centigrade for the bacteria cultivation. Okay, and I'm stopping in between, like if you have any doubts in between or something like that, you can put it in a chat and we can discuss it after the session. Okay, I'll be very happy to answer all the questions. And coming to back to the topic, then it was covered from the outside, and at the top of it, the motor was provided. With this motor, the shaft was attached, so that actually we cannot just put the inoculation like bacteria or nutrient growth and make pouring into the water and leave it like this. Okay, if we leave it like this, there will be biofilm formation. Okay, so we need some uniform formation of bacteria. So bacteria suspension, we can say. So this solution, if you can see, it looks like rasna. Okay, so at the top of it, sorry, there was some internet issue. Okay, so aerobic condition, to maintain the aerobic condition for bacteria, like we provided holes. Okay, and initial temperature of water was maintained 30 degrees centigrade, and after that 10 liter inoculum. Inoculum is already prepared bacteria हम दही जमाते हैं घर पे, we use at home. Milk, we put a little amount of, or how it got prepared. Similarly, that fancy name is, can say. So we the new solution rotated up to 28 hours. Okay, it was rotated up to. I'm here in the campus right now also, and I'm all memorizing that thing. The whole night I was going to the site and I was collecting the samples. So it was really very interesting. And if you get a chance to do such a large thing, you are lucky. Okay, so I'm feeling right now lucky, and I'm doing the seminar here only while sitting. So it is quite nostalgic too. So up to 0 to 8 hours, the growth was quite slow. It was working around, you can say, slowly. Okay, so that is called as the lag phase in the bacteria growth. And after that, it's left and right increased. Okay, so that is, we can say, exponential phase of bacteria growth. Okay, so up to 8 to 16 or 18 hours, there was exponential growth. And then after that, the stationary phase occurred, means the growth of bacteria and death of bacteria became the similar. Okay, so that is the stationary phase, and after that the death phase increases, like a bacteria optical density getting reduced. So these are four major phases of bacteria which are observed and which are generally there. Okay, and we can say at the optical density of 2, this solution was provided into the biotreatment tank. So in the biotreatment tank, like initially the arrangement was gravel layer was placed and a polyester filter layer was placed, sand was filled, then to expel the air voids, water was provided, and then after draining out the water for 24 hours, as I say, this is bioaugmentation, and bacteria needs to be attached with the soil for 24 hours. Bacteria solution was provided into that tank. Okay, and after that, urea solution and calcium chloride dihydrate solution was provided to the soil up to 7 days. Okay, and in every every day, 10 to 12 hours, biosparging was conducted, and every 12 hours of 24 hours of interval, this cementation solution was provided. Okay, so this is the image in between the treatment, and this is the after treatment. And after the treatment, dynamic cone penetration test was conducted at different 20 locations into the tank. Okay, and calcite precipitation at various locations was also determined. So our major aim was to achieve the uniformity of calcite precipitation along the depth. So along the depth, the uniformity was achieved, though at the central locations, and near central locations are where these location are getting the solution from nearest 4 injection points. So that's why here the amount of calcite precipitation was higher. So we concluded that like spacing of injection pipe can be increased to achieve the uniformity in calcite precipitation horizontally too. Okay, though otherwise like a significant amount of calcite precipitation was achieved throughout the depth. Then dynamic cone penetration index was determined, like depth of penetration of cone by number of blows. So at the center zone, the DCPI value was found lesser. So lesser DCPI value means higher is the denseness of soil, and higher denseness because of the higher calcite precipitation of the soil. And through IS 1893 codal analysis, we also determined that this sand, biocemented sand or biotreated sand, was found non-liquefied. Okay, so the aim of liquefaction mitigation was achieved in this study. And then like I just elaborated you the hazard mitigation. Okay, now we can talk about the environmental protection, because I wish to cover both the things. Okay, so for environmental protection, like I showed you the slide of soil pollution and soil contamination is there. Okay, so what we did over here, generally to standardize the things, we do like we provide the fixed amount of contamination to the soil. We contaminate the soil into the laboratory, and then we analyze that this methodology is working or not. So I worked like on 3 type of contaminations: zinc and chromium, and in different concentrations. Okay, like 1000 mkg, and the mixed combination of zinc, chromium, these kind of combinations were also provided, but the concentration that I detail, and now on 9th day and till 18th day we were the soil. Okay, so there were some control samples placed, not injected. Clear? So if okay, so those are just to check if we do not provide the bacteria, what will happen. So there was no change in hydraulic conductivity, neither nor on 18th day. So hydraulic conductivity was almost similar to the initial hydraulic conductivity. And then in the clean sand, if I say you, so in the clean sand, like we can say where the no contamination was provided. So without any contamination, the hydraulic conductivity reduction was higher. Okay, the maximum reduction in hydraulic conductivity either on 9th day or on 18th day, the reduction in hydraulic conductivity was higher. It means, and as compared to the contaminated soil, it means that the contamination is still affecting the bacterial growth. Okay, now coming to the results of contaminated soil like lead, zinc, and chromium. So zinc was found more toxic as compared to the chromium and lead. That's why the hydraulic conductivity reduction was less in zinc, and in chromium it was higher, and in lead it was intermediate. And also the concentration 1000 mg per kg and 2000 mg per kg. There is a difference. Okay, 2000 mg per kg, higher amount of contamination. So if it affect the bacterial growth, so lesser reduction in permeability. Okay, the same thing happened like in the other strength results also. Like a 3-layer calcite precipitation, like uniformity is still a matter. Okay, and in all the combination, uniformity in calcite precipitation was achieved, but in zinc contaminated soil samples, what happens, the amount of calcite precipitation was bit lesser, or in multiple combinations where the zinc was present, the amount of calcite precipitation was lesser. So this the zinc was found highly toxic to the bacteria. And then ultrasonic pulse velocity and unconfined compressive strength of soil and calcite content. These things were compared and analyzed. So in the clean sand where no contamination was there, the UPV was more than 2400, and the other contaminated samples, these are 1000 mg per kg contaminated sample. These are also have more than 1800 meter per second UPV. And the effect of contamination more can be seen in 2000 mg per kg sample, and zinc was found quite toxic here also. So that's why the calcite precipitation got reduced. Clear? So according to the criteria, it is like if any NEHRP, okay, National Earthquake Hazard Reduction Program. So in according to that, if the UPV is greater than 1500 meter per second, so it is of hard rock class A category, and if the UPV is in between 750 to 1500, then it is of hard rock class A, class B category. Okay, so I mean to say, like, its strength is similar to the sandstone. Okay, even in the if the presence of contamination is there. So this is how the MICP works. And similar, the relation has been seen with the UCS, a clean sand having higher UCS than the contaminated one, and in the contaminated also 1000 mg per kg contaminated sample have the higher strength than the 2000 mg per kg. Okay. And the relation of ultrasonic pulse velocity and UCS with calcite content, like with the increase in calcite content, it is in journal also. This is correlation was developed with the we can say contaminated soil, but with the non-contaminated soil too. With the increase in calcite precipitation, the ultrasonic pulse velocity and the unconfined compressive strength increases. Means that calcite precipitation is a hero of this process. Okay, if calcite precipitation is there, everything can be done, but it should be uniform whenever it is required, the uniformity, or if the thick crust layer is required, then for wind erosion, then it should be there. It can be dealt with the different amount of urea and calcium chloride dihydrate, as I say. Now, this is like toxicity characteristic leaching procedure testing, and initially we determined the soil pH, as I said, and sir said, like pH plays an important role. So if this range of pH can be achieved, like it shows that the calcite precipitation achieved into the soil media. And like we see that how much amount of calcite is leachable through the immobilized soil. So it was observed like 94% of chromium was immobilized, and 92% of lead was immobilized, but zinc was found due to smooth stone formation. The zinc was found immobile, like it was leachable. Clear? And because the pH of that solution is quite lower than 5. Okay, during the leachability testing, so it won't be stable, zinc Smith stone. Now, through the XRD results, like in the clean sand, calcite peaks were observed, and in the lead contaminated sand also, calcite peaks were observed, and in the zinc contaminated sand, zinc carbonate was formed. So, and in chromium oxide Cr2O3. Now, here the main point which I wish to want you to see here, like I augmented or I contaminated the soil with chromium 6, that is highly toxic and mobile. Okay, so now due to this mechanism and due to this process, it converted into chromium 3. So that is less toxic and not mobile, okay, immobile. Clear? So that's how this process works in the contamination immobilization. And next is like SEM analysis. So in the scanning electron microscopy also, you can see these discrete sand grains. Okay, these are untreated sand grains, and these are the biotreated sand, clean sand. Okay, the crystals you can see, and crystals of contaminated sand you can see. There is a difference. Okay, so but the calcite precipitation occur and strength was improved. We can analyze like a type of crystal and morphology of crystal. We can analyze through these methods, and it gives us an idea to conclude basically our why is lesser in contaminated soil, why this strength is smaller size crystals are there and they are less intact, then the strength will be lesser or ultra now these findings. And now coming to like there are multiple applications and metal contamination. For heavy metal contamination, we have done one more study, like only for lead contamination, consortia, using consortia of algae, nostocomion, and bacteria. So two type of bacteria, especially and Bacillus asphericus was used along with the algae. Okay, and then soil was treated. So because if you have heard about the stromatolite formations near the beaches, now near the beaches, some rock kind of formations automatically formed, but in million of years. You can Google search stromatolite. I think Shark Bay Beach, Australia. It is there. Okay, so from after getting inspired from that, I get to know like this kind of mechanism work. Okay, so algae was provided along with the bacteria, and that is called as consortia. Except if we provide both things together, then we can say it consortia. So through that, 99% of lead immobilization we have. Okay, so you can go through that study also, and other that like hazard mitigation, we have developed permeability reduction and converting sand into rock and enhanced oil recovery. In this enhanced oil recovery now since 90s, it is going on. The work is going on like that, and reclamation of old structures and sculptures and monuments, because monuments and sculptures are the heritage of our India, and we need to protect that. So this can be done over there too. And industrial wastewater treatment and calcium rich content or these things and urea content that can be used. And bearing capacity, ultimately we are improving the strength, so bearing capacity is increased. And internal erosion where we see this problem in the through the body of them and below the body of them, this is the major issue that can be reduced from this method. Okay, and fugitive erosion control we can see, and contamination immobilization I have already discussed. So my whole presentation is complete now, and generally I now I started like giving my expert talks on these things, because recently I got many things in my pocket. So I'm happy with that, and I'll try hard to do more. But my one more aim is there, like whatever I felt at that time when I was doing research, and how I motivated myself, how my seniors, my teachers, my friends motivated myself. So I wish to keep it going on, and I have something for you to inspire you and motivate you. And I think I'll do this throughout my life to inspire people. So this is my feeling. I don't know what ma'am will say. Sorry, ma'am, if I do it wrong. But it is like my feelings versus PhD work. I wrote, ma'am, do not know this. I wrote it 8 months of my PhD when I was small scale test when I was doing. So in that, I wrote it, and this is the exact copy paste of uh, my work. Okay, which I wrote. Hello, is it fine? Can you see? I think my slide is not open yet in your. Okay, so yes. So this I wrote when I was working on that large scale tank setup, and I was just about to write my thesis and last papers. So what I feel throughout my journey of PhD, or after that, even in my postdoc too, it was applicable. So if you are happy, you need to do research and write papers. If you are sad, if you have any kind of feeling, because feelings we cannot control, we are human, okay, but we can decide what we need to do at that time, and it will impact later. Okay, if we keep taking things, no, I'm sad today, I'll not work, I'll not work, so that won't help us, because tomorrow also you have some other kind of mood, and again the thing come to you, and you need to work for that. So, and same thing, this is not for research scholars only. Either you are preparing for competitive exams, IES, UPSC, anything, state government examinations, anything, because emotions come at any stage, at any, even after a second, I can get any emotion. Like I feel like if my son calls or someone said something to me, I'll get hurt, or I'll blame myself, or something can be happened. So in that case, what we need to do, first of all, we need to think what we were doing, and what will impact, like if we leave it in between, because the COVID time taught us a lot. Okay, if ma'am motivated me a lot to come to the campus, because in the COVID time we were there in campus, we were there, like our lab was whole lab present over here, and I acknowledge the support of my friends also who were there with me, in my Nitin and Meenu. So this friendly nature you should adopt. Okay, you should support your friend also, and you should also support yourself, get motivated from them also, or yourself also, to achieve the things in your life, and never ever think that you cannot achieve, because in any situation you can achieve, but sometimes the time is not right. Okay, that's why we sometime got failed. Today I was thinking to write my list of failures and my list of achievements. So my list of failures are more, even till now. Okay, and the list of achievement, but whatever I achieved, like that is a thing to be shown. Okay, so just work hard. There is no solution of work hard. Like without that, you cannot do anything. Okay, so just work hard, and if you have any problem, now just discuss with your friends, seniors, family, and get resolved it as soon as possible, and then again start work hard. And one more thing I recently learned from Reddy sir, that is his goal is like work hard and party hard. So I'll follow it in future also. I work hard and party hard. So we should work like that. And thank you so much. With this, I'll end my session, and I'll say all the best to you all the participants. Whatever you are doing in your life, just try to give your best shot. And if it is not a best shot, don't worry. You tried now. That is fine. Okay, you'll achieve one day. Thank you so much.
Thank you, Meghna. So we can have a couple of questions from the participants. So you can
Yes, ma'am.
message it in
Yes,
the
ma'am.
chat box, or like you can just ask her. Meghna, you can check the chat
Yes, ma'am. Yes,
and
ma'am.
reply accordingly.
This is. Anyone can ask directly to if or raise your hand if you want to speak, because the audience is participant is large. So if you want, you can raise your hand and we can uh, uh, work on your query and we can discuss it. And personally also, if you need any suggestions and anything, because some of you are either of my same age or my juniors, okay, and you might have any things, so we can discuss. How to deal with the situations is also a thing in life.
Proceed to the next talk by Professor Reddy.
Yes, yes, ma'am. Yes,
So,
ma'am.
no worries if you get queries later. Also, tomorrow also, Meghna will be here participating all 5 days. So please feel
Yes,
free
ma'am.
to interact. She'll be happy to, explain her work. So thank you so much, Meghna.
Thank you, ma'am.
So
Thank you, ma'am.
this sure.
Thank you, ma'am.
So we'll invite Reddy sir for the second lecture of the today's session. So, sir.
All right. Yeah. So I don't know if the problem is with my internet. I see some messages saying that internet is slow, but hopefully, can you hear me well or?
Sir, it's fine to me.
Okay. All right. All right. So, it was very nice to hear Meghna presenting her research. I had watched her research progressing over her PhD years, and Professor Nilima and Meghna were incredibly hardworking, incredibly efficient in spite of the COVID problems we had last few years. And I am really glad because of her hard work and enormous amount of time that she has spent in the lab. She was able to finish her PhD in 2.5 years or 3 years, 2.5 years, and with a lot of publications accepted or published by the time of her defense. So she is the role model to be a PhD student. If I had a student like that, I would be really, really lucky. So it's very nice to see her and motivating other people also. And I didn't realize that if you are sad or you have to write a research paper, I didn't understand that one, but maybe I should recommend my students, whenever they are not feeling well, they should start writing a paper. I thought writing a paper would make them cry, but you're saying that it will make you happy. So
Sir, sir, actually, when we write now, we have a feeling like we have done something. So a tick mark is there, like I need to do this work, and if that is get done, like I'm happy. It
yeah,
is like that. And we can listen music in that time if we are sad now. So music
yeah,
can divert our mind, and then we can start working.
that's nice. That's nice. That's nice. So all the PhD students who are listening, just get advice from her on how to be uh, efficient and accomplished. So, all right. Again, I want to show, as I mentioned yesterday. Um, so, I wanted to present uh, more, typical research projects that I conduct. I said I will select two topics related to remediation and two topics related to waste management, and then one topic related to sustainability. So yesterday I talked about problem of contaminated sites, and then the technology, electrokinetic remediation technology, research on that, um, and hopefully um, you got some ideas on doing additional research on that topic. So my goal is to let the typical projects that we work on and how we work on, and hopefully that will give you ideas in terms of research approaches, or even any additional research that you could be doing on the specific topic that I'm presenting. So today I'm going to talk about a technology using nanoscale iron. So this is a project that is funded by National Science Foundation, U.S. National Science Foundation, similar to in India, Department of Science and Technology. So always, the hard work is done by graduate and undergraduate students. So as you see here, Kenneth Darko Kajia, he was my PhD student who did his PhD work on this topic. And Paul Roots, you see here is an undergraduate student. So we really like to involve undergraduate students to make them learn research and motivate them to pursue graduate studies. And Anmant Kulkarni was my another PhD student. Uh, his research was on something else, but he helped on this project. So we always help each other in our lab, even though a project may be PhD of one student, but other students will help, and when the other students need help, rest of the lab will come and help. So we have a very collaborative spirit in our lab. So this is one of the projects, and the whole idea, as I said, I've given a lot of webinars when I go to some conferences and some colleges. You have students that may not have research experience, so I try to be more general. But today, I realize that attendees are PhD students or faculty with some research experience. So I'm taking the liberty to go into a lot of technical details. So what I'm going to do is give you some brief introduction to this project and identify, the need for research, and then research objectives and our research methodology involved various tasks. And I'm going to show the results of those. And then recently, I've been working with some Brazilian research collaborators. So again, they got to see my publications and they expressed interest in working with me. So I have been collaborating with them on the same topic. So finally, some overall conclusions. So um, here is when you say nanoscale, what do you mean by the size, right? So here is the typical size of particles that you see. The human hair is 60,000 to 120,000 nanometers. The fly ash is 1,000 to 100,000 nanometers. The viruses is 10 to 100 nanometers. Nanoparticles is 1 to 100 nanometers. DNA is 2 to 12. So you can see this. So what we are dealing with is the nanoparticles that range between 1 and 100 nanometers. So yeah, nano means 10 to the power of -9. And there are different particles, fullerenes, metal oxides, dendrimers, and quantum dots. So these are all nanoparticles. If you talk to anybody in material science, they deal with these kind of materials. Physics, material science people, are involved in synthesizing these type of nanoparticles and characterizing them. And these are used for different purposes. So the nanoparticles would be different than macro scale particles. So if you have nanoparticles, for example, let's say nano iron, nanoscale iron versus macro scale iron. So nanoscale iron would have different properties than macro scale iron. One of the things is, if it is nano, you will have increased surface area per unit mass. And also there are a lot of quantum effects resulting in unique mechanical, electronic, photonic, and magnetic properties. So that's the advantage of using these nanoparticles in different applications, including TV monitors and all kinds of electronic applications. So there are different chemical forms of common elements. So zinc oxides, titanium oxides, nanotubes of carbon, so many different types of particles that you can see. So as I said, these nanoparticles have a lot of applications in environmental field for remediation purposes. And for monitoring and detection of the contaminants. Environmentally benign process to monitor the contamination and reduce material energy and cost. So there are a lot of applications of the nanomaterials. However, there are implications or concerns with the nanoparticles. The potential toxicity. Are the nanoparticles toxic compared to the macro scale particles? Potential exposure, how if humans or any kind of ecology gets exposed, what will be the impacts? The fate and transport and transformation, if they are in water, how are they going to spread? Or if they are in the soil or groundwater, how are they going to spread? The bioavailability, bioaccumulation, and the critical metric is particle size and per number, or morphology, surface area, or functionalization. So these are all kind of issues that one has to be careful when you're using these nanoscale particles. So in terms of environmental applications, nanoparticles are used for air contaminant remediation, detection of the pollutants, and pollutant prevention. So titanium oxide is the one that is commonly used for water treatment, or purification or detection. Nano iron particles. I'm going to use this term NIP. That stands for nanoscale iron particles, or palladium and silver nanofilters, nanosensors. So those are the applications. In case of soils, if you want to use for remediation, you cannot use many different types of nanoscale particles. Particles, palladium particles, because you have concerns associated with the toxicity of those particles. However, in soils you always have iron. Any soil you take, you analyze, you will have a lot of iron in the soil. So since you already have iron, there is no problem using nanoscale iron particles. Of course, you want to see what will happen when you introduce it. Ultimately, where will it end up? Will it remain as nanoparticles, or will it become oxides? Or that aspect has to be looked into it. But just using iron, since you already have a lot of iron in the soil, so using iron is not a problem. So you cannot use other types of nanoparticles. And the groundwater is also the same thing. If you are want to remediate groundwater, you have to use nanoscale iron particles. You cannot use any other particles. I see a lot of research, publications that use different types of nanoparticles. Of course, and they say that they can be used for soils and groundwater, but in reality, nobody would allow you to inject uh, silver nanoparticles, or gold nanoparticles, or palladium nanoparticles, or copper nanoparticles. So because those could be toxic. You are introducing the contamination into the soil and groundwater rather than solving it. That's where you have to, when you are devising the research, you need to think about the practicality upfront. So if you do a lot of research and at the end you say, oh, these nanoparticles are toxic and you cannot use it. But in case of air and water is different. You have a control on nanoparticles. And whereas in soils and groundwater, once you introduce, you don't know where they are going. You don't have any control on them. So that's why, only nanoparticles that would be applicable for remediation are these nanoscale iron particles. So how do you make nano iron particles? There are two methods. One is the chemical method, so borohydrate reduction. So basically, this is the reaction that is used to create zero valent nanoscale iron particles. The other one is called the gas phase reduction by hydrogen. This is the one a company called Toda Kogyo in Japan. They create this one for electronic applications. Oxygenated iron sulfate solution, and then the geotite is reduced to alpha iron grains in a heated hydrogen gas atmosphere, and then that iron grains are wet milled to the size that you want. So during the wet milling, the surface converts to magnetite. So these are kind of the reactions that happens. So basically, you have a geotite is converted into uh, this zero valent iron particles, and if zero valent iron particles are mixed with water, then you will have Fe3O4. That's a magnetite. So that's how. So the nanoparticles would looks like this one. You will have an iron core inside, and then you will have this Fe3O4 shell outside. And during this process, you could have some sulfur introduced into that one. So sometimes in our studies, we saw that sulfur makes some difference. Okay, so this is the study we did it because the Japanese, let me see, the Japanese company was interested in Japanese company was interested in creating a new market for their nano iron particles. So and they also supported our NSF project as an industrial sponsor, and we able to get these nanoscale iron particles from them. So we didn't really synthesize, but we used the commercial ones. So you see this 70 nanometer is the average size. And this is the SEM image showing that how these nanoparticles will look like. And these are the properties of nano iron particles. The surface area, pH is highly alkaline, and surface area is, you can see 37.1 meters square per gram. And then, these particles, they're always, supplied in aqueous suspension. So basically, they put it in the solution, and they supply it. So it won't be like a dry. But later on, some other companies, they created a process where they can supply these nanoparticles under dry conditions. But this Toda America, the Japanese companies provide the aqueous solution, which is 20 to 30% by weight. So you see this one, the glass beaker you see, that's how you get the concentrated slurry from the manufacturer, and then you can dilute it and make any concentration that you want. So you're not going to use as provided by the manufacturer. So you're going to dilute it and then use that. So the density is 1.2 to 1.3. And also there is magnetic properties that you see here. These particles possess some magnetic properties. So these are the particles. And what is the advantage of using these in subsurface remediation, especially groundwater remediation? So one of the remediation technologies, as I mentioned in the yesterday's lecture, is the permeable reactive barrier. So let's say your groundwater is contaminated. You have a groundwater plume coming in there, and then you have it is spreading. Basically, you dig a trench across the contamination plume, and you put it in the iron. Most of the time, we put this called iron scraps or iron filings or scrap iron. If you go to any iron processing places, they create all this waste, and they are trying to find uses for those things. So you can just get these things very cheap, and then you put it in the trench. So as the water passes through that iron filings, then you have a chemistry that happens, and then contaminants gets treated, and your treated water comes out. So you have a contaminated water going into the trench, reacts with this iron filings. Iron filing is basically scrap iron, and comes out, the clean water comes out. So I'll show you the chemistry. Chemistry has been studied, and this remediation technology was developed by accident by researchers in Canada. But the biggest problem with this technology is that you dig a trench, right, and they put the material, and you have to wait for the contaminants to pass through the barrier. So the natural or site hydrogeology is going to control the treatment, because the water has to flow through that. So it may be groundwater flow in general is very slow. So it will take a long time. And then if this iron is exposed to atmosphere, the iron gets oxidized, and the reactivity of it will be reduced significantly. So that's the problem. And this technology is the most preferred technology compared to any other technology for groundwater remediation. Why? Because you dig a trench, you put this low-cost material in there, and you walk away. Compared to, think about pump and treat. You have to put the wells, you have to keep pumping, and what do you do with the pumped water? So huge operations are constantly going on at the site. So this one, that's the active remediation, and this one is kind of a passive remediation, because you don't have to do anything. You just dig a trench and put this material, and let the water pass through slowly, and remediation happens. You don't have to have anybody out there to do any maintenance, right? So this is a problem with it. But the problem is, as I said, it's going to take a long time. What happens if the hydrogeology changes, right? Instead of plume coming through this one, if it bypasses, then putting this one becomes useless, right? So that's the danger with this technology. So reason why we, this is a macro scale iron, so we have to put it in the trench. So the macro scale iron looks like gravel, fine gravel, or coarse sand, So that's the gradation of that. So instead of that, if I have a nanoscale iron particles, right, then what I can do is I can put a well into the contaminated zone, and I can inject my nanoparticles. because nanoscale particles, the suspension that you have, that can be injected under pressure, under gravity, whatever it is, and you inject into the contamination zone, and then the contamination reacts with the nanoiron particles and remediation happens. So you can put not one well, maybe multiple wells to encompass the entire contamination plume, and then, the contamination is going to be gone. It's like tagging the contamination. Whereas here, it's more passive, right? And we cannot inject this one. This is the macro scale. For example, if you have a fine gravel, how can you inject fine gravel into the sand, right? Through well, you cannot do that. But nanoscale particles, you can. It's like a very suspension, very fine particles, and you can make the slurry and put it into the well, and you can inject into the contamination zone. So this is and the reactivity between the contamination and the nanoiron particles is very, very quick. It's just a matter of introducing the nanoiron particles to the contamination zone, and the reactions will happen really fast. So very rapid remediation that happens, and then nanoiron particles can be injectable, right? And you can treat different types of contaminants, using this. So it's an enormous advantage, So you don't have a risk of contamination bypassing your remediation, and remediation taking long time. Whereas this one, you are attacking the source. So put the wells where contamination is found, inject it, and be done with it in a very short period of time. So this is the main advantage of using nanoiron particles, and very rapid cleanup, not wait a long time. The chemistry between macro scale zero valent iron or a nanoscale zero valent iron would be the same. So this, when I mentioned before, you have oxidation reduction reactions that remediate the contamination. So here, what happens is when you have iron is introduced, you will have iron corrosion reactions, and it will generate the lower redox potential, generates the hydrogen, and it's not going to be toxic to any contamination that you have in the groundwater or in the soil. And so iron, zero valent iron, acts as a reducing agent. So there's basically here, biologically also, see, bioremediation is also oxidation reduction reaction that is induced by microbes, mediated by microbes, whereas this one is chemical oxidation reduction. So this is going to be much faster and achieve the same kind of a result that you do it. So here, this one, nanoscale iron is used mainly for chlorinated contamination. The chlorinated contamination, basically organics that have chlorine molecules in it, they are highly carcinogens, highly toxic, and they don't degrade easily. So what we are trying to do is with this iron particles, we are dechlorinating them. So removing the chlorine will come out, and the chlorinated organic compound will become hydrocarbons. And if it becomes hydrocarbon, microbes can easily biodegrade. So it's kind of, achieving that risk-based levels, or reducing the risk by first dechlorinating the contamination, and then following that by the bioremediation. So this introduction of the nanoiron particles will dechlorinate the chlorinated compounds. So that sounds good, right? So, but we have problems with using the nanoiron particles. What are the biggest problems? See, these nanoiron particles, they don't want to be existing at the nanoiron particles. They try to attract each other. They agglomerate. Agglomerate means, they come together and they become aggregates. And then as you saw, the density is higher than 1, and they settle down, sedimentation. Even in the container, if you take it and they try to, come together, form these lumps, and then they settle down. But, if you have that kind of a problem, you cannot introduce it, right? So you cannot transport in the soil, and the reactivity, based on the nano size, when it agglomerates, it won't be nanoparticle. So that's the problem. And the transport in low permeability soils is difficult. Even if particles exist as nanoparticles, the pore space of clays is so low, then in the transport of these nanoparticles will become a challenge. Okay. So low permeability soils, if I have it, if I have a sandy soils, it's okay, I can inject it. But if I have low permeability soils, then the problem comes. Then how do we monitor and detect during the remediation? So I'm introducing nanoparticles into the ground, but how do I know where it get distributed? Where are they going? Are they going to the areas that I want, or are they going bypassing my area, right? So how do we monitor? Those are the challenges. And also, before we inject it, is there any way that we could predict the transport of soils when you inject into the ground, right? So a lot of models are for are there, but nanoparticle transport is not analyzed. So we see that a lot of advantages of nano iron particles, but we also realize that the challenges. So the research is to address those challenges, because the benefits outweigh the limitations. So if we can do some research and address those challenges, then we will be successful in remediating a lot of contaminated sites. So first thing that we need to do is make sure that nano iron particles, if I have in suspension, they remain in suspension. I don't want them to be agglomerating and then settling down to the bottom. Then then you don't have a nano iron particle suspension. That's not good. So how do we keep these nano iron particles in suspension? So for that one, we need to use a dispersant, some kind of dispersants that we use. Like an example is, that hydrometer test that we do, right? Sodium hexametaphosphate. Why do we add that one? We want to separate out the clay particles and want to see the particle settling, right? By separation of the particles. So the same thing, we need a dispersant like sodium hexametaphosphate, but that is for different application. Here we need to think about different type of dispersing solutions or dispersing agents that can separate out the particles, not allow them to come together and clump and then settle. So then how do we, transport that one? So what we did is we did a lot of evaluation and found that lactate modified nano iron particles are stable. So lactate is a kind of a very friendly dispersant that you can use, and it can also help in follow-on bioremediation. So we found something really, really safe, and in fact it helps in the follow-on bioremediation. Okay, so if you add this modifying agent like lactate or some other dispersant, the reactivity might change. So how do we quantify the reactivity of nano iron particles without any modification? And if I have modified with the lactate modified nano iron particles, how would they react? What is the difference between those? So we looked at two contaminants. PCP is pentachlorophenol, that's one of the toxic contaminants. DNT is also very toxic, and we looked at those things. And then there are a lot of other. So how do we quantify the extent of transport and reactivity in hypermeable zones contaminated with PCP and DNT? And then so we did some 1D column experiments, but then we wanted to look at the 2D because contamination could be spreading in the flow direction, but also could be dispersing in the transverse direction or vertically. So we wanted to look at how that could happen. And then, as I mentioned, the low permeability soils, we cannot, hydraulically inject these nano iron particles. This is where we use the electrokinetics. In the last lecture, I talked about electrokinetics. Electrokinetics can be used as a delivery system. For example, even in MICP, the people are thinking about, how do we introduce these microbes or any other, supplemental ingredients through electrokinetics can be delivered into low permeable zones. So let's go through these tasks slowly and see how we try to do these things. So um, let's first thing is we want the nano iron particles to be remaining in the nanoparticle state, not agglomerate and settle. So for that one, we try to do small scale experiments. So this is my lab. Somebody was asking me about my lab, how it looks. This is in one of the lab rooms. I will show you the video of my lab sometime in future lectures. Maybe it's, I have like a 1 minute video or 2 minute video of my lab. I can show you that. So how do we do this one? What are the dispersants that we can use, right? So the objective is, we want nano iron particles in a dispersed state, right? So that we can make sure that they can be injected into the soils and they get transported. So what do we do? So basically, we do some column experiments. You see the column experiments here. Basically, you have a small column here, and we can put the nano iron particle inject into the soil, and we can inject from the top, and then see how it is going through it, right? And basically, we will use the different types of dispersants and type of dispersant, concentration of that one. And then nano iron particle, as I said, source concentration is 20-30%, but we use the diluted concentrations. And we want to look at the effect of pH, effect of ionic strength. And the zeta potential, is measured using this zeta meter. That's important to look at it. The surface charge makes a lot of difference in terms of this agglomeration. So here is the small scale column experiments. You see there's a small glass column, right? 2.5 centimeters in diameter, height is 30 centimeters. And then basically we place the soil, this is the field soil, or any soil that you are interested, you can put it in there. First, we are looking at the permeable soils. Again, we are injecting into the sandy soil formations, not like clays. You cannot, if you have a clay, if you put a clay in the glass column, and then if you put some solution into that one, it's not going to go anywhere because of the low permeability, right? You know how you do the permeability test. So it is a sand permeable material. So you put it in the top, and then it should go through it. So basically, what we did is we prepared the sand column, and then we injected, certain amount of nano iron particles. So let's say 2 grams per liter concentration, and 35 milliliters is the 1 pore volume. So if I flush that one, how much is coming out. And then, we put that on the top, and then we flush the simulated groundwater, and then we analyze what is coming out, pH, EC, TDS, and iron that's coming out through this one. So if iron was transporting through the sand, then you would get those things in the effluent. If it is not, then, you will not see the concentrations in the effluent. So very simple, the setup here. So here is the close-up view of the testing. So bare nip, I use the term, basically bare nip is unmodified nano iron particle, right? So here, the soil column that I'm showing you close-up view of, and then we put 1 slug of nano iron particles. Remember what I said here. So we have a 2 grams per liter, 35 milliliter solution of that. We put it on the top. We basically inject from the top down. And then, we see, how much of it, and then we flush with the simulated groundwater through that one. So this should be going through it, if it is in the suspension form. But as you see here, bare nip, unmodified nano iron particles, they sit on the top of it. Nothing is moving through it. We applied 24 volumes of flushed water. We are flushing the water from the top and trying to get this one into the soil. And we even applied the pressurized condition, 30 psi pressure. We applied 30 psi pressure, 24 volumes. The water was going through it, but this iron was not going at all into the sand. If that is the case, it's useless. If you want to put it in a field application, if you have a well and you want to put the iron in it, and iron is just going to sit in the well, it's not going to go into the formation where the contamination is there. So this is totally demonstrating that you need to somehow modify these nano iron particles to be able to transport through the sand formation. So what we do is we try to look at a different uh, types of amendments. So the reason here, see, concentration of the bare nib. So we have 2 milligrams per liter, 4 milligrams. So different concentrations we took it, and we measure the zeta potential using the zeta meter. And you can see there's a lot of positive, uh, charge on these nano iron particles. You see the nano iron particles, you have a lot of positive charge, and the positive charge reduces as the concentration increases, right? And then the pH would increase here with the concentration, and then conductivity also increases with the concentration. So just showing, that the solution, nano iron particles, you get a stock as high concentrated, and then you're diluting it. You will be using, some range. You may getting 20%, 30% as a stock solution, but then you need to dilute. The lower the concentration, better it is in terms of the economics, right? So what is the optimal concentration of nano iron particle solution that we need? But look at that. The concentration itself will have impact on the zeta potential, pH, and conductivity, and that will change a lot of different things during the reactions. Okay, so we know that these bare nano iron particles, we cannot use it. So we need to make sure we add something such as sodium hexametaphosphate. So not exactly that one, but here we are using this aluminum lactate, sodium lactate, ethyl lactate as dispersants. And then we looked at two acids, aspartic acid and polyacrylic acid as a dispersant. And then we use these three types of cyclodextrins based on some, a lot of literature review and looking at their properties of this. Nobody has actually, did any testing with the nano iron particles with these kind of dispersants. So this is a time when, Professor Claudio Camaseye from University of Vigo, he came on sabbatical to my lab, and he spent 1 year with me. And so, he did it, all these experiments. So we evaluated all these dispersants. So the chemical structure of these dispersants is this one: aluminum lactate, sodium lactate, and ethyl lactate is the top one, and aspartic acid and polyacrylic acid is this. And you have these three, different cyclodextrins. Cyclodextrins are like a nice kind of a compounds. They're supposed to work in. They have interesting mechanisms of trapping the contaminants or complexing the contaminants. But here the goal is not using them directly for remediation, but using them to disperse the nanoparticles. Okay, now, out of this one, which one is good? Out of all these things, right? So we have all these potential options, ruling out a lot of different things. And also you need to choose something that is non-toxic. Again, you need to always keep in mind the practical applications. So can I use, let's say I use the dispersant, if it is toxic, and it may be a good dispersant, but you cannot use it. You cannot use a toxic amendment into the ground. So these have to be environmentally friendly, and of course they have to be cheaper. And can they work, right? So the whole idea of our research now would be, okay, which of these are good dispersants for nano iron particles, and what should be their concentrations, right? So we do this test. So we basically adding lactate, percentage of nano iron particles. So you have whatever the nano iron particles you have, the percentage of that. Okay. So So if I increase the percentage of this lactate and different types of lactate, aluminum lactate, sodium lactate, ethyl lactate, and sodium lactate, you see that one, right? So just increasing the lactate content. So look, we are looking at the zeta potential. So you have a positive charge. And if I use this ethyl lactate, you see this, the surfaces are becoming even more positive. And sodium lactate, if I use it, it's kind of the same and slightly decreasing. Whereas if I use the aluminum lactate, you see that it is decreasing significantly, right? So the surface charge of these, the nanoparticles would be decreasing, right? And here with the cyclodextrins, you see this. There's not much change in the surface charge, zeta potential. They're all like slightly increasing it. And then you look at this two acids. Two acids are showing a decrease in surface charge, and this polyacrylic acid is showing significant lowering of the surface charge and actually changing the surface charge from positive to the negative. So this is how we find it. Okay, what is the significance of this charge? Because if it is positive, right, um, then the particles are going to be attached to the soils, right? Let's say if the soils is negatively charged. So we will look at those results as we go through it. So also we looked at, so basically we want the positive charge to be reduced, right? So that they can be expelled to each other, and then we looked at the effect of pH. So you saw that one in the previous case, aluminum lactate. We used 10% of NIP, and then we looked at what is the effect of pH. So we control the pH, change the pH to 12, and looked at the zeta potential. As you see, pH effect is significant. As the pH increases, the charge increases, and then after a certain pH, the surface charge decreases. So the pH also has effect in addition to the concentration. Now, what about the ionic strength? So if I use a deionized water, so my zeta potential is this. And if I use the synthetic groundwater, basically, synthetic groundwater, we looked at the composition of it, and then we created that one in the lab. And then we used the different controlled ionic concentration, 6 millimolar, 10 millimolar, and 50 millimolar. But as you see, deionized water, you have a positive, more positive, and then when you use the synthetic groundwater, is lowered. And you can see as the ionic strength increases, it is kind of almost the same, but then at higher ionic strengths, it will have a significant impact on zeta potential. So but these are all in suspensions. So these aluminum lactate 10%, we looked at it, right? So here is if you look at here, lactate content, we looked at it. So we fix the lactate content, but we look at the concentration of NIP. So all of them have a 10%, but the concentration is higher. So previously we had fixed nanoiron particle. Again, you see that the zeta potential decreases. Bare NIP, you see that one, it decreases. And if you have aluminum lactate 10%, it decreases, slightly increases, and then it decreases. Again, you will see a lot of shift in the pH values depending upon the concentration, depending upon the type of lactate that you're using. Aluminum lactate 10% or bare NIP. And here what I'm showing is the pH is 1 and conductivity is the other numbers that I'm showing. This is interesting results. A lot of times what happens is we do the experiments in our lab using the deionized water. We think deionized water is idealistic, water, we don't have a lot of impurities, and we don't know the effects of those. Uh, and groundwater is as ionic strength, So what we did is we did the deionized water. So you see deionized water, you after a certain amount of aluminum lactate, um, the decrease will be less, but you can see the zeta potential decreases, right? But initially, uh, you know, it's high and then it decreases. But if you use the groundwater from the beginning, if I use the uh, groundwater with no aluminum lactate, still my zeta potential will go down. And adding the aluminum lactate will not change this one. It keeps the zeta potential much lower. So the whole idea here is that we want the zeta potential to be less positive, so that it can so these nanoparticles can be in suspension. So doing the experiments with the deionized water, you actually get the worst results, whereas the groundwater, which is close to reality, you get a better result. So I suggest, I mean, we do that one in our lab. We do the deionized water, but we also do the synthetic groundwater to see the effects of the water composition. Now you see that one. Now, I want to see these dispersing solutions. Will they help in removing, in transporting the contaminants? So initially, I had a sand in the column, and we put the slug of the nanoiron particle, non-amended, right? Just a bare nib. And after 24 volumes of the electrolyte solution, still nothing happens to this one. Just the electrolyte passes through that, and we collect it, and no iron can be seen in it. But if I use the 6% aluminum lactate in the nanoscale iron, and then put that in on the top of it, and then I flush the water, then you see that one. You see there is you see the dark black stuff with some thickness. That means nothing is moving. So here you see the less dark. So something is moving. If I increase from 6% aluminum lactate to 10% aluminum lactate, you see this? So there's nothing there on the top. So it's all of it has migrated through the sand. So that means, okay, bare nib, nothing is going to move. But if you have a 6% aluminum lactate, it's going to move a little bit, but not as much. But the ideal situation would be something between 6 and 10. So definitely if you use 10, a lot of that nanoiron particles could be transported, and then that is evident from analysis of the effluent that comes out. So we did those experiments, and iron concentration in the effluent, you can calculate how much we put it on the top, how much it came out into the effluent. So as a percentage of aluminum lactate. When you use the bare nanoscale iron particles, you get something eventually, you keep flushing it. But when you use this aluminum lactate, you can see a lot of, this basically more coming out from the bottom. That means, more of nanoparticles are coming out. Again, if you use the synthetic stone water, so even the bare iron could be transported somewhat compared to the deionized water. So this is for the lactates. This is for aluminum lactate, which we found better. And then methyl cyclohexene that showed slightly reducing positive charge, that shows this. And then aspartic acid, basically based on that zeta potential measurements, these three have the options. And then with the different percentages, you can see, up to 80% of the nanoiron particles that are introduced from the top could be collected in the bottom. The 20% is retained or trapped in the sand. That's fine, But at the end of the reactions, that becomes the iron oxides, and similar to other oxides you have in the soil, they remain in the soil trapped. So this is the column experimental results. The bare nib, if you take, you put it in the column and you try to flush with this pour water, nothing comes out in the solution. Nothing comes out in the solution. But if you use this aluminum lactate, 2%, 4%, 6%, you see that a lot of it comes out within, the two pore volumes. So a lot of it is available for the transport. And once, you get exhausted, then you get a zero in the iron. So a lot of iron comes out within, 2 to 4 volumes. So that's good. So what we found based on these experiments is that bare nib easily agglomerates and it will not be able to transport in the porous media. And dispersants will change the charge of the bare nib, and depending upon the type, concentration, and the pH. Different dispersants behave differently, as you saw that one. Out of all these things, what we found is the like aluminum lactate. We are lucky to find at least one that is robust, and to prevent agglomeration and allows the transport of nanoiron particles in the porous medium. And important thing that we found in these experiments is that the pore fluid composition is extremely important. Groundwater. Um, Ionic strength of the pore fluid affects the surface charge and transport of nanoiron particles, but contribution of other processes such as surface complexation reactions that also contribute to the overall transport. So I hope I made it clear why we need a dispersant. And then with this part of the study, we came up with aluminum lactate as the solution to the problem. Best thing. Now, that's all done, in the small column, but does it have a potential to be stable and be transported to the different types of soils? That one sand we used in the small column. What about different types of soils, even different types of sands, right? So for this one, what we did is we did this horizontal column experiments. So here is the soil column, laid horizontally. And then from one end, basically, we are flushing it. And then other end, we are collecting it, okay? So, from probably we collect, flushing from the other end, here is there's a top reservoir where we are injecting that one from one end. And then we are collecting the effluent from this end. And what we have here is, this magnetic susceptibility sensor. Basically, it can, sense the iron concentrations. So the problem is, when we're flushing, we want to know how that iron is transporting, nano iron particles are transporting. That's we are interested in. How do we know that one? So, you can run for a longer period of time, then all that iron will come out here, right? But if you want to know how it is migrating through the sand, you have to do experiments at different times, take it out and section it. Can we kind of monitor non-invasively, right? So basically what we do is we flush this one, and this magnetic susceptibility sensor is on the track. You see the track here? And then we move that one from one end to the other end, and then we take the readings of magnetic susceptibility. And that is correlated to the iron content. So, in the beginning, you can see the iron is coming, you will see the readings detected. And as iron moving, basically you can measure the MS values depending upon how much it's moving. Based on that, you can look at it. So look at the transport, dynamic transport of the iron, how it is transporting with time. So we did these experiments to look at the effect of porous media. So the sand is not uniform sand, right? One, you may have the fine sand, medium sand, coarse sand, well-graded sand. So that will affect, the transport of the nanoiron particles. We wanted to look at the porous media, even though it's sand, but different types of sand. And then effect of flow rate, what is the flow rate? Could you have higher flow rate or low flow rate? And then we wanted to do the modeling to, predict that transport using the advection dispersion equation and then DLVO theory. So this is schematic of this one is here. So again, showing the MS, this the sensor, this is the reader, and your nanoiron particles are injected through this reservoir into this one, and we are trying to collect what is coming out here. So this is the, during the experimental program. So again, we have nanoiron particles here, and we're injecting it. You can see the dark color here, and it's coming out here, and we're collecting for different pore volumes, what is the effluent that's coming out, and we will analyze what is the, how much is the iron in it. So this is again the schematic of this one. So basically we have a iron nanoiron particle suspension that, it could be bare nanoiron or lactate amended nanoiron, and then it's flushing through it, and is the magnetic sensor that's going through it. So this is kind of a cell. So what we did is we try to investigate the type of porous media, right? So the coarse sand, coarse field sand, medium field sand, and coarse Ottawa sand. This is more processed sand, like fine Ottawa sand. So this is from the processing plant, and these are actually field soils. And then we characterize the percentage fines, you see it, average particle sizes, based on the grain size distribution. These are all SPs, and SPSM. So this is the CFS is coarse field sand. This is the coarse Ottawa sand. C means coarse, okay? FS means field sand, and OS means Ottawa sand. So these are the different particle size distributions of it. And here are the results of this one. So what I'm trying to show you is, after a certain time, we take out the samples, and or during the experiments, remember that magnetic susceptibility meter I showed you. At time t, different times, we are measuring that one using the magnetic susceptibility meter. What is the change in the magnetic susceptibility, right? You see that one. There's not much change here in the using the bare nanoiron, right? So here is also, there's not much change. Here is also not much change. Here also 4 different sands, and doing with a bare nanoiron is not making much difference. But if I use 4 grams per liter lactate modified nanoiron, or 4 grams per liter for NIP, you can see this, and then 1 gram per liter NIP. So you can see this one, you can, concentrations, this is from the inlet to the outlet. See the with different times, t equal to 3 minutes is here, and in 10 minutes, this becomes, you look at 210 minutes, see a lot of iron has transported into the the sand. So here is 4 grams per liter NIP. Basically, this is non-modified, but you see most of it gets a little bit into the sand, but most of it gets, initially when you're prepared a sample, it is in suspension, and then it's able to transport certain distance, and after that, it aggregates and settles in the soil, and you don't see much, transported at all. Whereas here you see the transport, happening really good. This is for 1 gram per. This is for 1 gram per liter NIP. It's not, again, this 4 gram per liter and 1 gram per liter. There's not much change in the magnetic susceptibility, but it clearly shows that, if you have a lactate modified nanoiron particles, these particles are moving through the sand very nicely. So this is kind of a small visualization pictures. This is a 4 liter, lactate modified 4 grams per liter lactate modified nanoiron particles with the flow velocity of 1.2 centimeter per minute. So we're injecting it. You see this one, the color of this. So that shows that it is transporting. The good part of this research was, these nanoiron particles are dark in color, so you can visualization becomes easy. So this is during the column experiment. See, this is the magnetic susceptibility sensor meter. When I use the lower the flow velocity, and this is basically lactate modified. This is a non-modified lactate. So when you can see this one, it's uniformly going through it. Whereas here, you can see most of it comes into the soil sand and then agglomerates and settles here. So nothing goes. See, this sand here is very clean. So this one is transporting very nicely. This one is transporting nicely to uniformly through the sand. And this is the advantage of using some non-invasive techniques. You can reduce the number of samples. You know what's happening with time also. So we were able to do this test. Okay, with the magnetic susceptibility sensor, we can kind of get an idea how the iron is moving, how much extent it is moving. So under different conditions. All right. And then visually also, the medium field sand here, fine Ottawa sand, and then coarse Ottawa sand and coarse field sand. You can see how the transport is happening in, we hide this one. So, you can see that lactate modified transport that's happening. So coarse Ottawa sand at different times, you see that, okay, in the beginning, 9 minutes, it came inside, 20 minutes, it came more, 30 minutes, much more, and then 100 minutes, you can see it transported uniformly across the column. And we can measure the concentrations at the end. After you done the test at the end, you can take out the sample and cut it into sections, and then you can see how much is the iron retaining in the soil. And of course, you can analyze the effluent, how much is coming out, but a lot of this iron could be trapped in the sand. That's fine. We don't have to worry about that much. But the whole idea was we want to be able to have iron throughout the sand. So the bare iron, nothing moves. With 4 grams per liter nano iron particles, a little bit movement, but 4 grams per liter LM NIP, you see substantial amount going in there initially. And then with the time, you can flush it through it. So these are, depending upon the sand type, right? We are looking at the sand types here. So depending upon the sand type, you can see different amounts of the nano iron particles going into the sand. And then actually there is a correlation between magnetic susceptibility reading and iron. So you don't really have to measure the iron concentrations. If you can measure the magnetic susceptibility just by exposing the sample under the sensor, you can read that reading, and then that has a good correlation to the iron content. So we did the modeling, so we used the advective dispersive with a reaction term. So this lambda term is there, and this is kind of general. So this is the governing equation. So you have diffusion, dispersion, advection, retardation, and reaction term here. So the reaction term, represents that trapping of these nano particles in the sand. So we have applied these initial conditions, boundary conditions. You get this solution, and then we try to model it and then compare with the experimental results. That's not so bad compared to this one. And then DLO theory, also we used it to consider the efficiency of this thing. So these are different parameters, transport parameters. And again, the transport parameters depend upon the sand type that you're using as DLO. So you can read our papers to understand more about this one. The whole idea is, okay, we did the experiments, but we can also do simple modeling to be able to predict the observed results. So you don't have to, repeat so many experiments. With the experiments that we conducted, the modeling works fine. And, if you have conditions that are not tested, you could use the modeling to predict those results. So now the question is, okay, the conclusion is that lactate modified nano iron particle can be transported nicely to the different types of soils. Now the question is, we didn't really look at any contamination in the soil. So when you modify the nano iron particles with some dispersant like lactate, it basically forms the coat on nano iron particles and reduces that attractive forces between the particles. So that's how it is keeping the suspension. But if it is coating the nano iron particles, will it reduce the reactivity, right? That the reaction is with the nano iron, elemental iron. If you are covering the elemental iron with some coating, will it reduce the reactivity? And that's the purpose of our testing, to look at it. So the idea is to look at reactivity of the contaminants. So we looked at the kaolin as like a low permeability soil, and the coarse field sand as another permeable material. So there's one extremes, low permeability and high permeability soils, and we spike these soils with these contaminants PCP or DNT, and we look at okay, what is the effect of adding the lactate modified nano iron particles versus nano iron particles. Basically, we do the batch experiments, right? So, of course, in the field, we want the transport, but to look at the reactivity, so we can take the spiked soil and add our solution, nano iron particles or lactate modified iron particles, and mix them, and then analyze the samples at different time intervals. Okay, so the whole idea is, hey, is our nano iron particles are reactive or not? So we can always do this nano iron particles, SEM images and TM images to look at their morphology. So here is the reactivity results. So here is the reaction time. This is a DNT. I'm looking at the contamination is DNT here, and this side is the PCP. So the reaction time is, see this one, 4 grams per liter NIP, this one, and 4 grams per NIP degradation or removal. Basically how much is contamination is actually remaining versus the loss based on that. So nano iron particles, bare nano iron particles are very reactive. So you have very high reactivity. Most of it gets degraded, right? So 90% gets degraded. But when you add lactate amendment, the reactivity goes down because of covering the surfaces of the nano iron particles. It reduces. And then you see with time, in nano iron particles will slightly increase their reactivity, goes up to 100%, right? And look at what happens to lactate amended nano iron particles. So reactivity is low, and let's say if you allow the time, okay, reactivity is increasing, and if you allow more time, reactivity increases more. If you allow more time, eventually the reactivity of lactate modified iron particles becomes same as unmodified nano iron particles. So what is happening is, with time, the lactate coating is disappearing. And after a certain time, that lactate coating is completely gone, and the reactivity is equal to bare nano iron particles. So this is good or bad? This is good. In our case, what happens is we have to inject modified iron particles in the well, and we need some time for it to be transported into the sand formation. And then after transporting into the location that we want, if the coating goes away, that's fine. Because now, the lactate coating is gone. We don't want to transport anymore further. And then, it's as good as bare nano iron particles, and the reactivity is high. So what I'm trying to say is, this lag time for the removal of lactate coating really helps us, or gives us the chance for the nanoparticles to be transported into the sand to the distance that we want, and then the reactivity goes up. So the conclusion is, if you modify the bare nano iron particles, that are highly reactive nano iron particles with lactate, it's going to reduce the reactivity, but the reactivity will be recovered as the coating gets removed. And so that's the kind of conclusion that we got out of this one. So kind of very interesting results with the PCP, also similar things. So now question is, okay, lactate modified nano iron particle was found to degrade the organic pollutants in soils. Now the question is, what is their reactivity while transporting through the soils? This is in the small, the flask, right? The batch experiments. But hey, if it is transporting, is the lactate amendment is disappearing right in the beginning, then we know that it's not happening because it's getting transported. So, but will we get enough reactivity as it is transporting? That's the main reality, right? When you want to inject into the ground, we want it to be transported, and as it's transporting, we want to maintain the reactivity also. So for this one, we did the column experiments. Basically, simply what the difference is, before we mixed everything together in a centrifuge tube, right? But here we have a column and we are injecting this one. So here is before I showed you the transport experiments, we used the clean sand. Our interest was to look at how the nano iron particles will migrate. The difference here is I am contaminating the soil with a select contamination. Now I'm trying to flush through this one. So now I'm interested in how much it is transporting nano iron particles. At the same time, how much it is, remediating it. How much is the contamination reaction is happening, and it's, remediating. So we did that one. And then also one thing that important is, as it is transporting, you have a trapping of nanoparticles, and does the permeability change? So this is the interesting results on effect of permeability. So let's say if I use 1 gram per liter nano iron particle, right? So here is 1 gram per nano iron particles in unmodified 1 gram and 4 grams. So this is 1 gram and 4 gram. So 1 gram, you don't see much, reduction in the permeability, just slight reduction. But if I use 4 grams per liter unmodified nano iron particles, you see the permeability after certain pore volumes decreases significantly, because those particles got agglomerated and trapped and blocking the volume, pores, blocking the porosity. Whereas if you use the 1 gram per liter lactate modified particles, that's this one, you see the permeability remains the same, slightly decreases, but it's okay. Even if I use high 4 grams per liter lactate modified iron particles, the permeability remains high. And it's not clogging up like this one showing. If I use the bare nano iron particles of 4 grams per liter, it's going to clog up and it's not going to move further. Whereas 4 grams per liter, you see that one permeability is maintained. So the concern about clogging up the pores by these particles is not a concern if you modify it with lactate. So we did some experiments. Here is the time and the percentage degraded in the soil sections. We looked at that one, and what happens to the residual contamination? How much is remaining? How much is remediating? And then how much is degraded? How much is removed? How much is remained? So because remember, this is the chemical reduction technology. Through the chemical process, you are converting, you're dechlorinating it. So that's degradation. And then as you're flushing, some contamination may be moving out of the soil. That is the removal in the effluent. So overall, how much is the total remedial efficiency? You can look at all these things. And then you can model these things. So you have these model parameters a little bit different than the clean sand parameters. So again, we made another step and made progress, showing that, okay, lactate modified iron particles can be used to transport as well as get the reactivity. Now, that is column experiment, right? If you are just doing the standard experiment, that's fine. 1D column experiments is fine. But these particles have a density, right? So you may have particles trying to transport along the flow direction, but they are denser than water. They may be trying to settle down. So this is a 2D effects. So we want to know that one. If you do the small column experiments vertically or horizontally, you're not going to see that 2D effect. So what is the 2D effect? So for this one, we created this kind of experimental cell. It's like a tank. You see, this one is basically a tank. You will fill with the sand, and then you nip slurry, nano iron particles, modified or unmodified, and you inject into this chamber, and then you can pressurize it or allow the gravity, and let it go through here, and you collect it on the other side, and then look at it, how much is the volume that is coming out, and you can analyze the contamination concentrations that you have, or even iron concentration you can have. This is a simple plexiglass cell. As I said, you're putting the solution in the bottom here, and then it's coming out. Again, the top is sealed completely, and then you can pressurize it, and it's coming through it, and you have these pores through which you can collect the samples also. You can collect the samples of the pore water and analyze them. So this is how these things are. So basically, we run the tests under different pressurized conditions, and using the bare nano iron particles and lactate amended nanoparticles, we created uniform sand layers, and we also created the layers to look at the effects of heterogeneities. And So we got, interesting results. So, the pictures, you may not appreciate it, but during the experiments, you can clearly see it. What happens if you use the bare nip under different pressure conditions, see 1 psi, 2 psi, 8, So, with the pressure, we are pushing it into the sample. So best thing is to look at some videos of this one. So I'm showing here is, this is the bare nip, unmodified, and I'm using 0.8 psi. And same, unmodified nanoiron particles, but I'm using the high psi pressure. So basically, I expect this one to transport a bit less, and this one to be transported more, but still it's an unmodified. So you don't expect that one to be transported more significantly. So let's see if this video works. If it works, then it's good. So see this one, we injected from the bottom here, from one end, and this color is the black color is the iron. So it is a 0.8 psi. So it's just spreading only this area. In the 2 psi pressure, you see this one is spreading larger distance, but it's all heterogeneous. See, it's like not uniform. It's going, and then you flush it again, you see that, you flush it more, you see that one, it's coming out. But it's non-uniform. It's not, when we want to flush in the real world application, it has to be completely uniform, right? So this is the bare nip. If you don't, put anything, if you low pressurized conditions, get very less transport. Nothing comes out here. Nothing gets transported. But if you have high pressure, then you will have this random distribution that goes on. Now let's look at the same things with modified nanoiron particles. So this is a lactate modified nanoiron particles, right? So there's a low pressure, same low pressure and high pressure. So let's look at how this goes. So here I'm injecting the nanoiron particles from this end. You can see the distribution of this one. See the color, right? The black color is kind of a more uniform, and you see something coming out at 2 psi. It rapidly passes through it, and you see the color is pretty uniform. That shows that nanoiron particles are uniformly distributed, right? So kind of this the effect of same thing. The previous one you saw 0.8 psi, you didn't see much transport, but here you can see the lot of transport. But higher pressure definitely flushes through this whole entire the soil uniformly, and you can see nanoiron coming on the other end. So this basically I'm doing what I did. Those same things I'm showing. Here is the comparison. You can see 0.8 psi and the nanoparticle, lactate modified nanoparticles. It's a kind of I showed you, bare nanoiron particles at different pressures and lactate modified nanoiron particles at different pressures. What I'm trying to do here is just to understand. I'm just putting simultaneously same pressure, one with a bare nip, other one is the lactate modified nanoparticle. See the difference between these two. See the distribution here, see the distribution here. So this whole area is uniformly distributed, and it's getting here, unless it is so here you see it's nothing affected here. You injected another slug of the nanoiron, you can see things are going like this. Now let's look at different types of sands. So here look at uniform sand, right? And here you have two layers. The coarser sand at the bottom, and then you have finer sand at the top. And these heterogeneities are important to consider. So you can see this. It's not migrating at all. Here it migrates to the more permeable layer. That would be a concern. And here is the again the different layers in heterogeneity is going to be a huge problem. So you're going to get this transport through the high permeable zone, not so much from. So this is a uniform. If you have a uniform one, it goes through the entire thing, whereas it does not go. So it's basically the whole idea is here. If I have lactate modified nanoiron particles, can really help transport through the sands, and irrespective of type of sand. But if you have layered profiles, it's going to transport through high permeable zones. Now, the question is, you're not going to always have high permeability soils. You're going to have a low permeability soils. What can I do, right? To give up? No. So I'm going to use electrokinetics as a delivery system for delivering the nano iron particles. So for this one, we did this testing. So we could take the clay soil here. We have a nano iron solution here, and we inject it and apply electric potential. We try to transport that nano iron particle because hydraulically you cannot do it. It's a low permeable material. So we try to do this one. We contaminated the clay with the DNT, and we look at the iron distribution, pH, conductivity, ORP, and electroosmotic flow. We look at it. So this is kind of a setup, and we can see the electric current variation, electroosmotic flow variation, and then you can see, how the pH changes, and then what happens to the transport, right? So you can see substantial amount during the testing period. You can see substantial amount of nano iron particles getting transported um, through, through this soil sections, right? And so you can look at the residual DNT concentration, how much is reduced. He's talking. Okay. All right. So there's a pH change, how a pH change happens. So basically, these tests show that, electrokinetics can be used to transport the lactate modified nano iron particles if it happens to have clays. So that's all about our research. And, as I said, some Brazilian collaborators got to know about our work, and they wanted to do testing or research, to see if they can apply, in their locations. So it's a little bit different. That's what I suggest. You need to understand the local conditions and see how this technology can be tailored. So they have this is a review paper, and then we looked at the transport, reactivity, and toxicology of nanoparticles in Brazilian residual soils. So they're not worried about the groundwater. It's more on the sand, soil. They have a huge unsaturated soil zone, and you want to use these nano iron particles to treat the soils, right? So it's, how can we use the local ecological organic stabilizers? So this is the permeability test. First of all, you need to look at the soil that you get it. And they were able to have this traction machine where you can put 3 samples together and test it. So you're flushing this nano iron solution to the samples and then seeing how much is coming out individually from each of them. And then you look at the permeabilities. So, in this case, you see, and here, one interesting thing that we did it is the nano iron particles study that we did it a long time ago. Perhaps we were one of the first ones to work on this Toda America iron, and later on some other companies came into existence. There is a company in Czechoslovakia, the company that provides these nano iron particles. Now you don't have to worry about if you are interested in doing research on this one, you can contact that company. They can ship some samples initially if you want it for free, but later on, if you want to have larger quantities, you can buy them. So they have, like Nano 25. They have different names for their iron particles. They also provide, particles in a dry form, and they tell you how to mix it to make it a suspension. So basically, we got this commercial nano iron particles from Czechoslovakia. They got it, and then we tested at different concentrations. So 1 gram per liter, 20 and 27 grams per liter, 25 grams per liter, and 10 grams per liter. So you look at this one, if the concentrations are low, permeability is not changing. But if the concentrations are this high concentration suspension you have, the permeability is significantly low. That's one thing you have to worry. So you cannot use high concentrations. Then you will plug up the pores and hydraulic conductivity decreases. You cannot even flush anything. So you need to optimize the iron suspension concentration so that the permeability does not change. Okay. Same thing, this is the another type of nano iron they supply. They supply different types of nano iron with some kind of their own recipes. They won't tell you how they do it, but this is the nano 25S. And here is this one does not have a reduction, but some of these have a huge reduction. So you have to be careful in this one. So the whole idea is you want to be, closer to the low end, 1 gram per liter or 4 gram per liter is probably good. But if you have higher than that, the permeability is going to be compromised. You don't want that one to be done. And they tested with excellent chromium. This technology can be applied to chlorinated compounds and some excellent chromium or arsenic that you can change the valence state. So basically, you're converting chromium 6 into the chromium 3. So this shows the efficiency of this. And then, we did different pressures and, how the permeability changes, how overall chromium reduction happens. And then the question is, how do you see here we are talking about soil, unsaturated zone, right? So that all the flow and other things that we studied in our lab, that's not applicable. It's not a groundwater scenario. It's like a soil scenario. So you basically have to mix it. You have to have an injection system, like grouting. How you do the soil stabilization. It's like that. So the question is, how do we do that one? So these guys created this experimental setup where you inject it and and distribute the iron. So here is the injection point here, and you like grouting, right? So you have a nano iron particles. This is all water zone, no groundwater, and you inject it, and then you put these wells around, and you can collect the samples and see how much of distribution that you got. So here is their big tank that they had, and then distribution, and then you at the end of distribution you core them at different radiuses and different locations, and then collect the samples and test for nano iron concentration and contamination concentrations. So that at different depths, right, and at different radial distances, you can plot all the data and analyze what is happening to the contamination different depths, and also what is happening to the iron distribution. And you can create the 3D plots to understand the contamination degradation and contamination, the iron transport. And the toxicity is a big issue. Are these nano iron particles are toxic? So there was an investigation that is done to investigate the toxicity of nano zero valent iron particles. The gist of it is that they are not toxic. So there's these batch experiments were done to look at the microbial activity, and some simple evidence shows that they are not toxic. Now the question is, this nano and injection of these nanoparticles sounds like a very chemical intensive. Will it be sustainable? So that's where we said, okay, how can we make nano to be more sustainable? Obviously, bioremediation is sustainable, but bioremediation itself will not work. So can we supplement nano with bio? So that becomes a nano bioremediation. So this student, Zikel, he visited my lab for 1 year, and we did a lot of these studies in my lab when he was visiting. So the whole idea is, okay, it could be groundwater or it could be in the soil. We could be injecting these nano iron particles into the contaminated soil or contaminated groundwater. Now, what happens is, with the age of the nanoparticles, I told you, the reactivity goes down. The particles reactivity goes down with the age, and reactivity decreases when they get oxidized. So it's very important to make sure that we deliver it quickly when these nanoparticles are active. You don't want them to be passivated or oxidized under these conditions. The idea of nanobioremediation is bioremediation does not work when the concentrations are very high. So let's say you have a chlorinated organic contaminants, right? So you have the concentrations, nothing is happening, it's not degrading. And because microbes are there, but they don't want to touch this one because these are high concentrations. And then why don't we inject the nano iron particles? You inject the nano iron particles, and then you see the contaminated concentrations decreasing it, and you have a byproducts increasing. So as I said, chlorinated compound that you have, chlorinated compound is decreasing it, and then due to that reduction of a chlorinated compound, you're going to get byproducts. Basically, you get hydrocarbons. Hydrocarbons come up, increases. So the chlorine is gone, and they have C and H. And then what happens is, then now the microbes will like the environment. You don't have that toxic stuff around them, so then they become active, and they start degrading that hydrocarbons. So basically, this is called abiotic and biotic. Basically it's a non-biological process here using the nano iron. It's a more chemistry, and then here is more biology. So this will be very good, right? So you're using quickly these nano iron particles, converting chlorinated compounds into hydrocarbons, and this one is less effort. Only the effort that is needed is this injection of nano iron particles, just enough to convert the chlorinated compounds into hydrocarbons. And then after that, bioremediation, you don't have to do anything. You don't have to inject, you don't have to do anything. So this combination, if you don't have nano iron particles, the contamination is not going to biodegrade. So we need to add this nano to degrade this toxic contamination, or degrade the contamination to a certain level where the bio can happen. So this is the nano bio combination. So you have active nano zero valent iron particles, you have microbes, and you have this nano iron particles become inactive, and then the contamination byproducts that you have that can be attacked by microbes. So this is the one slide. Overall conclusion is that aluminum lactate is our new discovery. And lactate, if it was there, as I was showing you in this example, okay, I'm using the aluminum lactate. If the aluminum lactate is residing, that could actually work to benefit the bioremediation. So it's not bad. It's environmentally friendly, and we were able to understand the different system variables that affect the transport and reactivity of the contaminants in different porous medium, and we could use electrokinetics in low permeable soils. So there's a lot of research that can be done on this one. As I said, my Brazilian collaborators, they have their own situation slightly different than what we investigated in US. You could do the same thing. So there could be a lot of opportunities to do research in this field. Again, if you have a material scientist working on some materials that you could be potentially using for remediation, work with them. Or if you want to work on nanoparticles, they can be commercially acquired, or you can synthesize yourself and use them. So that's kind of my whole idea for this talk is to showcase how we do a typical project. And again, based on our results, our results were used by US EPA and some other industrial partners to apply in the field. I didn't mention other factor is that pulsing, even the lactate modified iron particles, instead of putting under constant pressure, so pulsing pressure, we found out that it can enhance the transport. So the results are actually, used by industry for field applications. I mean, we are not involved in it. We contributed to the science and fundamentals and proposed the solution. Somebody else was actually, trying to use it out in the field. So that makes it happy because somebody actually using your results for actual field applications. So kind of, wanted to showcase that research, how it is done. I hope it was not monotonous, uh, didn't make you sleep. So with that one, I want to end my presentation, and we have half an hour time, and me and Meghna can answer any questions that you have.
Yes, sir.
Let's have a discussion. As I said, as the Professor Nirma mentioned, it is a workshop. Workshop is where we need to have more talking and discussion. It's not a one-way presentation. So let me yield back to Professor Nilima or Meghna so we can have some questions. So let's give like a few minutes for the attendees so that they can type their questions in the chat box. Please type your questions so we can go over these questions, or you can unmute and ask your questions. So the question is, how would we, how would you, I would like to know how to determine the diffusion coefficients through experiments. So basically it's all fitting to the data. So basically you have hydraulic conductivity information, and I mean, if you want to do separate experiments, diffusion experiments, you can do that one. You can look at my book. So basically, you can take the column and horizontal column have the same equal water levels on both sides, and then put in a contamination solution in one side, and monitor the concentration decrease. And then after a certain time, you can section it and see the concentrations, and then you fit it to your only diffusion transport equation. So you can do, diffusion experiments, isolating the advection part. But if it is a reactive, then, reaction has to be accounted along with the diffusion. But in our experiments, we basically, use the inverse modeling to determine the parameters that best fit the experimental data. Okay, so we have a lot of people, so we need to see some questions or comments.
Yes, sir. We are expecting
Don't
few
don't
questions.
don't feel shy. I mean, just relax and type a question. What did you, if you have any questions or comments. Are you guys typing something? Anyone has any questions or comments? Yes, looks like I did a very good job that you don't have any questions.
Yes, sir.
Okay, everyone, type something to just show. I want to see if you are there or just, you logged on and disappeared. Can everyone type something? Say hello to me. I want to see
Hello, sir.
how many people are present. So can you type hello in the chat box? Just I want to
Hello,
see
sir.
how many people are actually listening. Okay, so just a 2, 3. 4 or 5. See how many people are there actively listening. Okay, very good. So yeah, so how I would like to know how successful field application of nanoparticles so far. It's really good, as I said, as long the main question is the delivery. Okay, the chemistry is well established. Chemistry is there. The question is, how do we deliver these nanoparticles into the contaminated zone, right? So yeah, even we did this research a long time ago, and there are a lot of case studies. US EPA document. There are publications on field applications of this. I think one of my conference publications also summarizes the field applications, and it shows that it really works. The whole concern is the delivery of it, and before they passivate, they become inactive. So these items, so you don't have to worry about these things. They're not going to go anywhere. So one of the problems is people who initially were concerned, like, where is he introducing these nanoparticles into the ground, they are going to, invade the subsurface, and we're going to have all kinds of issues. But as you saw from my experiments, it's hard to make them move, So, and once they oxidize, and they become iron oxides, and they become solids, and they get trapped. So it becomes a little bit of additional iron, not significant. I mean, you already have a lot of iron in this in iron oxides in the soils, and this adds on to a little bit more than that.
Sir, good evening, sir.
Yeah.
Sir, what about the long-term benefits of this nanotechnology, sir, for this the geoenvironmental hazard?
The long-term benefits are, like, the contamination is gone, and then the iron becomes iron oxide. So the contamination is already disappeared. I mean, like a detoxified. So you don't need to worry about the long-term effect, right?
Thank you, sir. Thank you.
If the contamination is gone, and then the introduced nano iron becomes iron oxide and becomes part of the soil composition, then you should not have any issues.
Thank you, sir. Thank you.
So there's a lot of opportunities to do research, using the, again, we have to be open. I mean, when you think about nanotechnology, you think nanotechnology is only for electrical, mechanical, material science people, in civil and environmental engineering, we don't use that one. That's not true. So there are a lot of applications of nanotechnology in civil and environmental engineering applications. Okay, I want to see some more of hellos in the chat box, just to see if you are there or not. If you haven't typed hello, that means you are just switched on and somewhere.
So someone asked, can we use for marine soil?
Yeah, you can use the marine soils, depending upon marine soils or clay soils or what? Probably clay soils, right?
Probably clay. Yes, sir. Probably clay.
Yeah. So basically, you have to use the electrokinetics, because if it is a low permeability material, you cannot really inject it. So you have to combine nano iron particles with electrokinetics, so that electrokinetics is used as a delivery system. And that's kind of interesting. So you can collect those soil samples and characterize those things, and then see if it can be transported into that. Will there be any effect on the fertility of the soil, plant growth after the application of the nanoparticles in the soil? So that's, I haven't shown you that results, but we also did effects of toxic. We evaluated the toxicity of nano iron particles on plant growth. So we amended the soils with different amounts of nano iron, and we tried to plant the soils, and we found out that there's not much effect. So as I said, like, these nanoparticles are not going to be remaining toxic forever. Somehow the air, when the air enters into it, then they get oxidized. And so the elemental form of nano iron is not stable. So it wants to convert into oxide. So once it becomes its oxide, then it will not have any effect. Uh, so that time frame to see how long that nano iron particles are in the elemental form. So you can also do the experiments like that, yourself. So you can amend the soil with a nano iron and try to grow the plants and see if there is any toxicity to the plant. I mean, it probably depends upon the soil, depends upon the plant, and see, application of that. Again, we're not looking at, surface application, right? We are looking at deeper applications. And so that may not be, I mean, anyway, you could have plants going deep into the soil, maybe into the contamination zone. If you treat it with nano iron, will it have effect? So you can make that one as a research project. So what are the treatment for brine solution after treating the soil with nanoparticle? I mean, brine solution is basically you're talking about effluent that comes out. So I'm assuming that. So as I said, like, you will not have any issue because, these nanoparticles are going to be trapped somewhere along. Our concern is just even transporting little bit distance. You're not talking about huge distances. So you're transporting to a certain distance and then having it reacted with the contamination and settling as iron oxide. So after flushing certain, the solution into the contamination zone, you will not see any kind of effluent problems. So what is the design life? Design life is you're talking about days. That's why you have to mix this solution right in the field and then inject it. So as I said, maintaining the reactivity of the nanoparticles is critical. And even if you have nanoparticles in the lab, if you just you have to seal it and keep it under no oxygen environment condition. So if you just open it up, they 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 don't remain as elemental iron. So it's very critical. So they mix it right away and then inject it, and reactivity happens very quickly. So you're talking about a matter of days, few days for nano iron to exist as a elemental nano iron at the most. Yeah, so you can, that's the question is, can this technology be used in industry before disposing the waste containment in the form of screen or filter unit? Yeah, you can actually. So if you are interested in using, um, you can use the scrap iron itself. That can remove a lot of contamination. So you don't have to use it in a nanoscale form. So the nanoscale form is suitable so that we can inject into the ground. But if we also did a lot of experiments on using scrap iron as filter material, and it's very good. It can take out chromium and other things too. So to answer your question, if you have waste or wastewater, you can use scrap iron that you can get from any iron stockyards, um, and use that one. So you're using the waste material that costs nothing for treatment. Can this be used to treat high iron content groundwater? No, because basically you're using the iron, adding on the iron, and it won't be dissolving that much, so it won't increase the iron content. But if you have a lot of iron in the soil itself, but that iron is in a different form, Fe+2, right? So that is not reactive. And if you have iron content groundwater, uh, so if you have a lot of dissolved iron, can I introduce the nano iron? That's an interesting question. You can probably, look at it. If you have a dissolved iron and you're using iron particles, how would it interact with the dissolved iron versus elemental iron? Yeah, so want to know nanoparticles effect on plants and soil, because we are using the metals for making the nanoparticles. So that's what I'm saying. If you cannot use the other types of, there are all kinds of metals that are used as nanoparticles for many different applications. But for remediation applications, as I was telling, for soil and groundwater, we're limited to nano iron. But in case of wastewater treatment or water treatment, you could, pass through the filters through this nano iron, or palladium catalyzed iron. There are different forms of nanoparticles, that titanium oxide. So you can use those things because you have a control. You're not allowing it to disperse. But when you're using the soil and groundwater, you have to be careful because you don't have a control on your thing. How long will nanoparticles be used and how much? So that again is they're not going to remain reactive for a long period of time. So that is actually the problem. So they try to become uh, I don't know, oxides. They are in the stable form. Um, so there's a lot of opportunities to do research in this area. So we are convinced that there are some people listening, right, Meghna?
Exactly, sir.
Okay.
You are listening. Even
So,
many. Mm.
yeah, so we can count how many people are. We can give extra grade for the people who said hello.
Yes.
Yeah, thank you so much. I mean, you really need to pay attention to some of these new ideas and then explore, what can you do as research projects. If you're a faculty, if you're a student, you can, try to explore a lot of different things.
Sir, Kavita is asking, like, does it affect the strength of soil as well?
Yeah, strength of the soil could be affected by taking more amounts. There are nanoparticles are used for uh, soil stabilization, strengthening, but it has to be probably in large amounts and mixing them. So there are papers, the soil stabilization with the nanoparticles. But what nanoparticles? Be careful. Don't use any toxic nanoparticles, to increase the strength. But then eventually, they might leach out and cause the contamination. You can do that. I think I've seen people mixing nanoparticles with the soil and stabilizing it. But the question is it worth it? Nanoparticles are expensive to make it, compared to other alternatives. Is it, cheaper, unsustainable option or not? But if you find something, you think it's feasible to use, if they are available and feasible to use it, why not? And you have to look at strength if you are interested in strength, and then later on you need to look at are there any other leachability issues that you need to worry about after mixing it. All right, yeah, we have a few more minutes. If anybody wants to add on, anybody, if you have any experience working with nanoparticles for any applications, you can say that. You can share that information. Okay, Meghna. So I see, maybe
Yes, sir.
give 1 more minute and see if anybody has any questions. You
Yes, sir.
can answer that.
Sure, sir.
So this is your last chance to ask any question.
Exactly.
And you can also ask, Meghna tough questions. How many of you are faculty members? Can you put it in the chat box, see if you're a faculty member? Just say faculty in the chat box. Just I want to see, if we have any faculty who is interested in doing research. Just in the chat box. If you're a faculty member, just type faculty. That should good enough. Yeah, it's good.
Yeah, it's good.
Excellent. So HBTU Kanpur.
Yes, sir.
Very good. On HAT, so that's good. So we have 3 faculty members, 4. So kids, Warangal, that's good. So we have faculty members that listening, I think. So yeah, great. See several faculty members. If you're a faculty member, just type in so that I
Yeah.
can see how many people are faculty. And this would be very useful for you. If you are looking for new area of research to work on. Start off with a literature review, see what other people have done it. I mean, obviously what you are interested in, and what work has been done, and then what you can do it. It's also like, what kind of nanoparticles are available to you. Okay?
Yes, sir.
So
I know Dr. Bharti from SKIT Jaipur. Like she completed her PhD from IIT Roorkee. I know her.
yeah.
Dr. Bharti, you can share your experience. There are other many faculties are there. I think a few faculties left because from Indore, from few universities, many faculties have joined.
So yeah, you guys keep in touch with me. I mean, I want to see at least a few faculty benefited by this and pass on the knowledge to a lot of students. So just frame your research, nicely so that it has some fundamental aspects as well as practical aspects of it. So very good. Okay, so I didn't waste my time.
Yes.
Some people are listening. So if some of you can take up this research, that is really, makes me happy to be able to present and pass on some useful information to the researchers. So tomorrow I'm going to talk about some waste management issues. Next 2 presentations are on waste management, tomorrow one and day after tomorrow one. And then I'm going to talk about sustainability aspects in geoenvironmental engineering in the last talk. So just listen to the presentations and yeah, I see some people are trying to think about what research they could do it, and it's nice. You should ask question whether it makes sense or not. Just no question is a dumb question. Every question is worth asking there. So I think we can wrap up, Meghna.
Yes, sir. Yes, sir.
You want to say any closing comments or anything? We have 4 minutes left, 3 minutes left.
Yes, sir. So thank you so much, sir, first of all. And today I presented, I think, first time in front of you. So
You
please
presented,
give, please.
you presented your PhD defense.
Defense, yes, sir. Defense was a different thing now. Like as a speaker, I present first time. So you can also give me some critical comments so that I can follow in future. And other things like I'm thankful to the participants for their patience, and they are replying and they are enjoying the sessions. And I'm getting personal messages also, and the direct message also. So thank you so much. So we'll meet tomorrow at exact 4:30 p.m. And if you have any doubts, so we can you can ask later on also. And someone was asking in the group that Geoenvironmental Practices group, like if we can provide daily recording of session. Actually, we cannot provide it daily. We'll give it to IGS, and there is a IGS YouTube channel, Indian Geotechnical Society. So they'll upload, and then we'll get the link, and then we'll be providing you. So it may take some time. So please be with us, and we'll share those links soon. But we cannot provide right now all the recordings or anything.
Yeah, recordings will be eventually available, but I think it's nice to participate and have some discussion. As you are listening to the presentation, if you have any questions, the best part is to interact with the presenter right then and there, right? So yeah, so I highly recommend you to attend the live and ask questions, anything you want to ask. So somehow all these presentations should be somewhat useful.
Yes, sir. And even later on, if any friend of yours or anyone is looking for a YouTube video and they've gone through these lecture, so they can ask, they can send an email to us, and they can ask us through the email. So that can be responded, right? So, but try to attend here, and then we'll see how to upload, and we'll provide the link. So only 1 more minute left, sir.
Yeah, we'll stay for 1 more minute.
Yeah.
So if anybody wants to, log off, that's fine. And then we will stay for 1 more minute until 7:30, and then we end it.
Yes, sir.
So thanks again, everyone, for attending it. We'll see you tomorrow.
Thank you.
Thank you. Thank you.
Thank you.
Thank you.
Thank you. Thank you.
Thank you. We are good.
Shall we close, sir, at 7:30?
Yeah, that's fine. Thank you. Thank you. All right. We'll meet up tomorrow.
Yeah. Yes, sir. Good night.